Hello, welcome back again for our last part of Chapter 1. In Part 4 of this video lecture, we will be looking at circular motion and centripetal acceleration. Let's start out with a little demonstration of what circular motion is.
Hello there. So we've got a tennis ball on a string, and I can demonstrate two types of circular motion here. If I spin the ball around in a horizontal circle like this, you've got uniform circular motion. And another way I can do it is to spin the ball in a vertical circle like this. Another example of uniform circular motion. In all cases here, the ball is going at approximately the same speed. It's not speeding up or slowing down. So that's what we mean by uniform circular motion.
So what you just saw was called uniform circular motion. This is when an object moves with a constant speed along a circular path. So in the demonstration where I was spinning the tennis ball on the string, the ball was moving at a constant speed. It wasn't speeding up or slowing down, and obviously the ball was traveling in a circle because of the string. So there are three basic properties of uniform circular motion here, and we'll be looking at some more later in this lecture. But to start out with, we can define what is called the period of the motion, and this is the time it takes for the object to make one revolution. So if we start with the object at the top and we measure how many seconds it takes for the object to go once around the circle, that is the period in seconds. And notice the period, we're going to use the uppercase T so that we don't confuse period with time. Time is lowercase t and period is uppercase T. The frequency is the number of revolutions or cycles per second. And the frequency and the period have a reciprocal relationship. So frequency is 1 over the period, and likewise the period would be 1 over the frequency. The last thing here is we can describe the speed of the object as it travels around the circle. The speed in meters per second, remember, is given by the distance traveled divided by the time, how long it takes. In this case, it's convenient to use for the distance to travel once around the circle. And this distance is called the circumference of the circle. And you may remember from your math or geometry class that the circumference of a circle is given by 2 pi r, where r is the radius of the circle. That's the distance from the center of the circle out to the edge. And then the time it takes for the object to go once around the circle is the period. Remember, that's the definition of the period. So the period is given by the uppercase T. So the speed of an object in uniform circular motion is given by 2 pi r over the period T. Now, since remember that the period T, or we could say 1 over the period T, is equal to the frequency, we can replace the 1 over T with F for frequency. So there's another relationship here that's convenient to use. The speed of an object in circular motion is 2 pi Fr. So let's look at an example and do some quick calculations for uniform circular motion. Dad puts his child on a cart attached to a rope 2 meters long. He spins the cart around and around in a circle. It takes 3 seconds for the cart to make a full circle. So you can see in the picture here, Dad's at the center. Here we have the rope, which defines the radius of our circle. This is 2 meters. And the child in the cart is going to go in a circle around Dad, and it takes 3 seconds to go around each time. So there's 3 questions here. The first one, what is the period of the cart? Well, since the period, remember, is just how long it takes to go around the circle, the period is just 3 seconds, which was actually given to us. Part B, what is the frequency of the cart's motion? Well, the frequency is 1 over the period, so we have 1 over 3, and that is 0.33 cycles per second. So in other words, the cart is going around 1/3 of a trip around, right? 0.33 is 1/3. 1/3 of a cycle every second. The final question, calculate the speed of the cart. There's two ways you could do it. Remember, we had two equations on the last slide. The one I used here was the speed or velocity is 2 pi fr. So we have 2 times pi, 3.14. The frequency we just calculated is 0.33. And the radius of the circle at 2 meters. So the product of all these numbers turns out to be 4.2 meters per second. That is the speed of the child in the cart here. Let's return to the case where I was twirling the ball on the string over my head like this. It was going around and around. But remember that the ball that was swinging around in the circle at constant speed, it doesn't appear to be accelerating because it's not speeding up or slowing down. But the ball actually is accelerating. The reason for this is that the ball's velocity is constantly changing direction, not magnitude. In other words, if we think of this arrow here as pointing in the direction that the ball is traveling, well, as the ball moves around this circle, that arrow is constantly changing directions. So, and it turns out that velocity, in more advanced courses, we look at velocity as something called a vector, which not only has a magnitude, which gives us the speed, but it also has a direction. And so since the direction is changing, that means the velocity, at least that part of the velocity, is changing. So this is a type of acceleration called centripetal acceleration. It's not due to a change in speed of the ball. It's due to a change in the direction of the ball. So one question that comes up is, what is the direction of this centripetal acceleration? Well, the string's tension force is pulling on the ball towards the center of the circle. And we're going to learn in the next chapter, in chapter 4, the relationship between force and acceleration. And the kind of the bottom line here is that the acceleration of an object is always in the same direction as the force that acts on the object. So we have a force due to the string tension here pulling the ball towards the center of the circle. So what this means is that the acceleration of this ball is accelerating towards the center of the circle. So this is a little bit more of an abstract form of acceleration. It's not quite as easy to visualize as just an object that's speeding up or slowing down. So this type of acceleration is called centripetal acceleration. Centripetal literally means center seeking, which means pointing towards the center. So whenever an object is moving in a circular motion, it is experiencing centripetal acceleration towards the center of the circle. And there's a nice formula here to calculate centripetal acceleration. Notice we still use A for acceleration. This little c here is sometimes put there just to remind us that this is centripetal acceleration. And the formula for calculating it is v squared over r. In other words, this is the speed of the object, or velocity. We square it, and we divide by r, where r is the radius of the circle that the object is undergoing. Now, in case you're wondering where this formula came from, that the centripetal acceleration is v squared over r, this is the proof or derivation of the centripetal acceleration. And I'm going to skip over this. We don't really need to go through the details of this in this course, but if you're interested in how I arrived at this formula, this is a pretty straightforward proof of doing the derivation for centripetal acceleration. Let's move on though, and we're going to keep in mind we'll use this result for the problems that we're going to see coming up. So here are two sort of quick examples of centripetal acceleration. So again, with the ball on the string, let's calculate the centripetal acceleration of a 0.1 kilogram ball swung around your head on a 1 meter long string once per second. So remember, in order to figure out centripetal acceleration, we need to know v and we need to know r. So to figure out the speed of the ball, the v, the velocity, remember that we have the velocity is the distance that it travels divided by the time. All right, we've already seen some formulas for this, and the distance is 2 pi r. That's the circumference. So 2 pi, and the radius this time is 1 meter, which is nice. And then the time it takes this is actually the period. I should use an uppercase T here. The period was given as 1 second, because remember, it goes around once per second. So our speed, and this one just don't do anything. We can cancel them out. And we end up with 2 pi meters per second. So now we can calculate the centripetal acceleration. V is equal to 2 pi, but remember we have to square that. So on our calculator, we're going to multiply 2 times pi. You have a button on your calculator for pi, or you can type in 3.14. That's close enough. And we remember to square that result, and then we divide by 1, which really doesn't do anything. And we end up with 39.5 meters per second squared. So this acceleration, remember that g, the acceleration due to gravity, is 9.8, or let's just say it's about 10. So this is about 40. So this acceleration of this ball is about 4 times the acceleration due to gravity. So one way we could describe this is that this ball is experiencing 4 g's of acceleration. All right, 4 times the acceleration due to gravity. Let's now do another example and calculate the centripetal acceleration of the Earth as it orbits the sun. So, as you know, the sun is in the center of our solar system, and the Earth rotates or revolves around the sun, and of course it takes a full year for the Earth to go around the sun once. That's how we define a year. So again, in order to calculate the centripetal acceleration, we need to know v and we need to know r. So let's calculate the speed of the Earth first. So we're going to do the same thing here. The velocity is equal to distance over time. So the distance is the circumference of its orbit, meaning it travels all the way around its orbit like this. So we have remember that circumference is 2 pi r. So we have 2 pi times the radius. Now the radius is the distance from the Earth to the sun, which you've maybe heard is 93 million miles. But of course, we need to convert that to meters. So I've done that here by looking up the conversion between meters and miles. So the distance from the Earth to the sun is 1.5 times 10 to the 11th power meters. And then down in the bottom here, we need to divide by t the period of the Earth's rotation around the sun. And the period, of course, is 1 year or 365 days, but remember, we have to convert that to seconds. So, in order to convert days to seconds, you have to multiply by 24, because there's 24 hours, and then by 60, because there's 60 minutes in an hour, and then finally another 60 because there are 60 seconds in a minute. So you end up with a lot of seconds in a year. But this is how many seconds there are in a year: 3.15 times 10 to the 7th. So we have just a big number here on top, a big number on the bottom. When we actually divide this out in our calculator, we come up with the speed of the Earth is about 30,000 meters per second. So obviously the Earth is traveling extremely fast as it orbits around the sun. Now, one question is, why don't we feel this speed, right? Well, remember, we don't feel speed. We can only feel acceleration. So let's now figure out what the acceleration of the Earth is as it goes around the sun. So centripetal acceleration is v squared over r. So here's our v, 30,000. Remember, that has to be squared, right? So this is going to get really big. On the bottom, though, is the radius in meters, which we figured out up here was 1.5 times 10 to the 11th meters. Now, this is a huge number. So when you actually do this on your calculator, look at the number we come up with for the acceleration: 0.006 meters per second squared. This is an extremely tiny, basically undetectable acceleration. And this is why we don't feel the motion of the Earth as it zooms around the sun. The acceleration is so small that it is undetectable by us. Here's another example of centripetal acceleration. Let's figure out what the centripetal acceleration of a car is when it goes and makes a turn on a road like this. So a car driving at 12 meters per second makes a right turn with a radius of 10 meters. So what this means here is, when you make a right turn, you're actually tracing out, this is called an arc of a circle here. It's a part of a circle. And the radius of this imaginary circle that you're driving around is 10 meters here, okay? So that's what we're going to use here for r. So the centripetal acceleration of the car, remember, is v squared over r. So v is 12, and remember again to square that, and we divide by the radius of the turn, which is 10 meters that was given. So this is actually 12 times 12 is 144, divided by 10 is 14.4 meters per second squared. Here's our last example and slide of this chapter. This is called Loop the Loop, and you've maybe been on a roller coaster ride like this where the roller coaster goes upside down on a loop like this, or maybe you've seen a stunt driver in either a motorcycle or car that's riding around a circular track like this and actually going upside down and not falling off the track. And of course, here with the roller coaster too, the roller coaster doesn't fall off the track and you don't fall out of the roller coaster. So what we're going to do here is try to figure out how fast you have to be going to safely go around upside down in a circle like this so that you don't fall. There are some different ways to approach this type of problem, but probably the simplest way to do it is what we're going to do here. And that is to think about what would happen if, let's say, this car were not going fast enough. Well, if the car weren't going fast enough, the car would fall. And now the car is in free fall. So it would be accelerating downward at g, which is 9.8 meters per second squared due to gravity. Okay, and obviously we can't have that. So in order to stay on the track, we require that the centripetal acceleration is greater than g. So in other words, a sub c must be greater than g. And we know a sub c is v squared over r, so we need that to be greater than g. So this is a simple task to solve for the velocity. We just multiply both sides by r to get rid of the r here. So we get rg on the right side, and then we take the square root to get rid of the square. So as long as the velocity is greater than the square root of the radius times g, which is 9.8, the object will stay on the track. And interestingly, you don't even have to have a seatbelt on. Of course, you wouldn't want to do this, but you would not fall out of the roller coaster without, even if you had no seatbelt, as long as your speed was greater than the square root of r times g. So the engineers that design the roller coaster obviously have to make sure that the speed of the roller coaster exceeds this value here, depending on the radius of this circle. Here for this one, here's the radius here. And they do these calculations obviously to make sure that the roller coaster is going at a safe speed so that it'll stay on the track. So we'll end up this lecture showing you kind of a fun demonstration using this type of information here where we can try to keep an object from falling out even when it's upside down. So enjoy the demonstration, and I will see you later in the next chapter. Goodbye.
So in this demonstration, I'm going to take this basket and put some tennis balls in there. Obviously, if I turn the basket upside down, we can see the tennis balls fall out. But one thing I can do now is let's try spinning the basket over my head upside down. And notice the balls stay in the basket. Now let's make it a little more interesting. I've got a glass of water here. You can see it's about half full of water. So I'm going to put the water glass in the basket. Let's do the same experiment here. here's our glass of water, still in there, and not a drop came out in the basket. Cheers.